right now, inside a massive manufacturing plant, there's likely a single piece of dirt.
Just floating around.
Yeah, just floating around. And I'm talking smaller than a human red blood cell.
It's completely invisible to the naked eye.
Right. And it's just quietly shredding the internal components of a $100,000 piece of machinery.
It's terrifying, honestly.
It is. And the craziest part, the operators walking past that machine every single day, they have absolutely no idea it's even happening.
Because they just hear the hum of the engine and assume everything is fine.
Exactly. So, welcome to the deep dive. Today, we're looking at a really detailed brief on the Sullair compressor fluid analysis program.
Which is fascinating material.
It really is. And our mission today is to unpack how taking a tiny, seemingly insignificant sample of machine lubricant can essentially act as a crystal ball.
A very highly engineered crystal ball.
Right. We're going to explore how interpreting the microscopic universe inside that fluid allows us to predict the future, maximize equipment performance, and radically reduce downtime.
We really need to establish the stakes here, though, because in the world of heavy machinery, manufacturing, industrial operations, unexpected downtime is just the ultimate enemy.
Oh, yeah. It's a nightmare.
It really is. We aren't just talking about a minor inconvenience. If a massive industrial air compressor fails, it doesn't just stop one process.
Right. It ripples.
Exactly. It can bring entire production lines and supply chains to an absolute grinding halt.
Millions of dollars just gone.
Yeah. So this deep dive isn't just about oil or chemistry. It's about a broader, highly effective engineering philosophy called integral predictive maintenance.
Integral predictive maintenance.
Yes. It is about capturing and acting on verified data to, neutralize problems long before they ever manifest as a broken machine.
Okay, let's unpack this. Because the core promise of the document we're looking at is explicitly stated right at the top. It says, reduce downtime and maximize equipment performance.
Which sounds great on paper.
Right, everyone wants that. But to actually achieve that, the source suggests you have to completely change your relationship with maintenance.
You really do.
Yeah.
Because most of us operate inherently in a reactive state.
Like with our cars. We treat maintenance like, waiting for our car engine to start sputtering and smoking on the highway before we finally decide to pull over and check the oil.
Yeah, we run things until they cry for help.
Which is terrible.
It's a remarkably inefficient way to manage any complex system. But the Sullair program, it flips that model entirely on its head.
How so?
Well, it operates more like giving the machine a continuous, comprehensive blood test to proactively manage its health.
A blood test for a machine. I like that.
Yeah. And the analysis evaluates the compressor fluid based on 3 foundational pillars.
Okay, what are they?
So you have the original formulation of the fluid, the consumption patterns within the machine, and the expected life of that fluid.
Okay, wait, I want to pause on that second pillar. Consumption patterns. What does that actually mean in this context? Because a machine doesn't consume oil the way an engine consumes gasoline, right?
No, it doesn't burn it for fuel.
Yeah.
But every machine operates under a totally unique set of environmental stressors.
Right.
You might have 2 identical air compressors.
Right.
But one is sitting in a pristine, climate-controlled pharmaceutical facility.
Nice and clean.
Exactly.
Uh-huh.
And the other is outside a cement plant, sucking in ambient dust and dealing with wild temperature fluctuations.
Oh, wow. Yeah, vastly different lives.
Exactly.
Yeah.
So how quickly a machine degrades its fluid, its consumption pattern, tells you an enormous amount about the specific, localized stress that machine is under.
That makes total sense.
And if we connect this to the bigger picture, this 3-pillar approach allows you to verify the exact remaining life of the lubricant.
Based on its actual working condition.
Exactly. Rather than just relying on a generic manufacturer's estimate.
So it completely eliminates the calendar as a maintenance tool.
It really does.
You aren't just looking at a whiteboard and saying, well, it's been 6 months, we should probably drain the fluid. The calendar is basically just a guess.
A very blunt, often very costly guess. When you rely on a detailed history of lubricant performance instead of a calendar, you can precisely optimize your changeout intervals.
Meaning you save money.
A lot of it. You tightly control your maintenance costs because you aren't throwing away perfectly viable, expensive fluid prematurely.
Just because Tuesday rolled around.
Right. And conversely, you aren't risking catastrophic mechanical failure by running severely degraded fluid for too long just because the calendar says you have another month to go.
Okay, so if this analysis is essentially a continuous blood test for a massive industrial compressor, what exactly are the lab technicians looking for?
That is where it gets really granular.
Yeah, like when they put this tiny vial of fluid under the microscope, what is the actual story they're trying to read? Are we just looking to see if the oil is dirty?
Oh, it's so much more than that. What's fascinating here is that the tests reveal two distinct parallel narratives.
Two narratives.
Okay. First, they decode the chemical health of the fluid itself, like, is the oil still capable of doing its job?
Right.
Second, they reveal the physical health of the machine. Are the metal components inside the compressor actually surviving the workload?
Oh, I see.
Yeah, and the source outlines 8 specific tests that make up this analysis.
8 tests in one little sample.
Yep. They do a water test, a particle count, a check on the pH level. TAN, which stands for total acid number, viscosity, contaminants, wear metals, and additives.
Okay, wait. I get tracking metal shavings. Like if I see iron or copper in my oil, obviously something inside is grinding together and breaking apart.
Right, that's straightforward wear and tear.
But why are we tracking the pH level and the total acid number? It's an industrial air compressor, not a swimming pool.
That is a fair point.
How does machine oil even become acidic?
Well, this raises an important question about the fundamental nature of industrial lubricants. They don't just sit there peacefully.
They're working hard.
They are subjected to extreme violence. Inside a rotary screw compressor, the fluid is constantly exposed to immense heat, high pressure, and massive shearing forces.
Shearing forces like it's being ripped apart.
Literally. Over time, that combination of heat and pressure causes the hydrocarbon molecules in the fluid to break apart and react with oxygen. They oxidize.
Wait, so the environment is literally cooking the oil and tearing its molecular structure apart.
Correct. And the chemical byproduct of that oxidation process is acid.
Oh, wow.
Yeah, that is why tracking the total acid number, or TAN, along with the pH over time is so incredibly critical. The fluid is supposed to coat the internal components and protect them.
Right, it's a lubricant.
But if the acid number spikes, the chemistry of the fluid has fundamentally flipped. It is no longer protecting the machine.
It becomes the enemy.
Exactly. It has become corrosive. It's actively attacking the internal seals, the bearings, the rotors. It will start to eat the machine from the inside out.
That is wild. And what about the additives test? Because the source mentions tracking additives, which I assume is related to this acid problem.
Spot on. High-end industrial fluids are blended with specific chemical additive packages.
Like armor for the oil?
Basically, they are designed to neutralize those acids as they form, fight off oxidation, and prevent rust. But those additives are sacrificial.
Oh, they get used up.
They get used up over time. By tracking the additive depletion rate, the lab can tell you exactly when the fluid will lose its ability to defend the machine.
Okay, let's talk about viscosity then, because the source specifically highlights tracking viscosity at 40 degrees Celsius.
Yes, that's a key metric.
Why are they testing it at that specific temperature? And why does the thickness of the oil matter so much?
Well, viscosity is simply a measure of a fluid's resistance to flow. It dictates how thick or thin the fluid is.
Right, like syrup versus water.
Exactly. And the 40-degree Celsius mark is a standard industrial benchmark. It mimics normal operating temperatures.
Okay, that makes sense.
Inside a compressor, the fluid's job is to maintain a microscopic film, literally a wedge of oil between heavy metal components spinning at incredibly high speeds.
So they don't touch.
Right. If the viscosity drops and the fluid gets too thin, that protective wedge collapses. You get metal-on-metal contact, severe friction, and immediate wear.
Ouch. And if it goes the other way, what if the fluid gets too thick as it degrades?
Then the machine has to work significantly harder just to pump that thick sludge through the system.
Just straining the motor.
Yeah. It creates fluid friction, which drives up the internal temperature of the machine, wastes a massive amount of electrical energy, and actually accelerates that oxidation process we just talked about.
It's a vicious cycle.
It really is. By tracking the viscosity over time, and the source actually shows charts tracking this from late 2009 through early 2011, operators can see the exact moment the fluid loses its structural integrity.
Okay, so we've covered the chemical side. Let's look at the physical health of the machine. You mentioned testing for wear metals and contaminants.
Right. Testing for specific wear metals, like iron, copper, or aluminum, tells the lab exactly which part of the compressor is failing.
Oh, because different parts use different metals.
Exactly.
Yeah.
Different components are made of different alloys. So if there is a sudden spike in copper, the technician knows a specific bearing is starting to give out.
Even if the rest of the machine is fine.
Yep. Testing for overall contaminants, on the other hand, reveals what is invading the system from the outside world.
The environment fighting back.
Yeah. If there's an unusually high amount of silica, which is essentially sand in the fluid, it tells you that the ambient environment is heavily polluted and your intake filters have failed.
The outside world has breached the closed system.
Precisely.
Here's where it gets really interesting, though. The source talks about the particle count test, and it specifically mentions looking for particles larger than 6 microns.
Which is unfathomably small.
It is. Just to give you some context on how small that is, a single human hair is roughly 70 microns thick. A red blood cell is about 8 microns.
So we are talking about things smaller than a blood cell.
Exactly. They are actively hunting for microscopic specks of dirt. Why does something that small even matter in a massive piece of heavy machinery?
It matters because of the engineering tolerances. High-end rotary screw air compressors are machined to incredibly tight specifications.
Like virtually no wiggle room.
Exactly. The gap between the rotors, or the clearance inside the bearings, might be just a few microns wide.
Oh, I see where this is going.
Yeah. If a 6-micron particle of silica gets past the filters and enters a 4-micron gap, it doesn't just pass through.
It gets stuck.
It acts like a wedge. It becomes microscopic sandpaper. It gets dragged through that tight clearance, scoring the metal, gouging the surface, and stripping away efficiency with every single rotation.
So a speck of dust smaller than a red blood cell can slowly murder a compressor.
If left unchecked, absolutely. It reduces the machine's ability to compress air, which means the machine runs longer, runs hotter, and burns more electricity to do the exact same amount of work.
But this brings up a massive logical problem in my mind.
What's that?
Well, knowing exactly what to test, knowing all about the total acid number, tracking the depletion of additives, hunting down the 6-micron particles, that is all completely useless if the machine fails while you're waiting 3 weeks for the lab results to come back in the mail.
You were absolutely right.
Like, if the acid is eating the machine today, finding out about it next month doesn't help me at all.
No, data without speed is just an autopsy.
An autopsy, wow.
Yeah, it tells you why the patient died, but it doesn't help you save them.
Exactly. Which brings us to the physical logistics of the Sullair program and how they bridge the gap between deep laboratory science and the messy reality of a busy manufacturing floor.
It's a very streamlined process.
The source details this highly specific process centered around a field sample kit part number 022501386667.
It is a very deliberate, very low friction system.
It has to be, right? Or operators simply won't use it.
Exactly. If it's complicated, it gets ignored.
So the kit includes just 3 things: a sampling vial, a postage paid shipping container, and a fluid sample information form.
Very straightforward.
You literally just draw a simple 150 milliliter sample, fill out the form, drop it in the prepaid box, and put it in the mail.
Right. But the magic happens once it arrives.
Yeah, the most critical part of this entire logistical chain happens at the lab. There is this great quote in the source material from Todd Torp of Bribazon pump, compressor, and vacuum.
Oh, I remember this one.
He says, "I can't believe I received the analysis report the same day you received my sample."
That same day turnaround is the operational linchpin of the whole program.
It changes everything.
It really does. Because if they can process the sample and generate the report the moment it hits the lab bench, they transform historical data into actionable real-time intelligence.
So you aren't reading a history book about what happened to your machine.
No, you were reading a live weather report.
That's a great way to put it. And the program doesn't just dump a spreadsheet of chemical data into your inbox and, wish you luck.
Which would be overwhelming.
Yeah. The text notes a really vital logistical detail here. The lab emails the complete analysis report to both you and your local Sullair distributor simultaneously.
Which is a brilliant approach to data management, if you think about it.
Why is that so important?
Well, imagine a facility manager receives a report showing their fluid of demanding. Viscosity has suddenly dropped, and the copper levels have spiked.
They might just panic.
Right. They might not possess the tribological engineering background to know what that actually means for their production schedule. Raw data can be paralyzing if you don't know how to interpret it.
Right. It's like getting the results of your blood test directly from the lab without a doctor there to explain what the numbers actually mean. You just see red flags and think the worst.
Precisely. By looping the distributor into the immediate communication chain, the program ensures you have an expert translator on standby.
Oh, so they decode it for you.
Exactly. The distributor reviews the results, provides the context, and gives you the basis for better maintenance management decisions.
They can actually give you a game plan.
Yeah, they can look at the data and say, hey, The spike in wear metals indicates a localized bearing failure. We need to schedule an inspection this weekend during your planned downtime, rather than waiting for it to seize up in the middle of a production run on Tuesday.
So they translate the raw chemistry into preventative action.
Exactly. They take the mystery out of it.
So what does this all mean when we pull back and look at the broader ecosystem?
That's the real question.
Because going through the trouble of mailing samples overnight, measuring particles at 6 microns, tracking additive depletion, all of this microscopic precision makes a lot more sense when you realize what kind of fluids they are actually protecting.
Right. These aren't generic off-the-shelf oils you just buy in a plastic jug at a hardware store.
No, they're analyzing a highly specialized portfolio of engineered fluids.
Very expensive, highly engineered fluids.
The source lists the specific proprietary products covered by this program. Things like Solube 24KT, SRF I4000, SRF II8000, AWF, and Pristine FG.
Those are all extended life fluids.
Right. They are designed to run for thousands and thousands of hours under extreme conditions. Which brings us to a much larger corporate philosophy detailed in the document.
The sustainability aspect.
Yes. Mailing a sample to a lab isn't just about saving a bearing. It's about reducing waste at a fundamental level.
It is about maximizing the life cycle of high-value resources. Sullair explicitly states in the text that a fundamental part of their leadership is a dedication to minimizing environmental impact.
In both the manufacture and the use of all their products, right?
Exactly. They are actively seeking new technologies for energy-efficient compressed air products and overall environmental sustainability.
And, it's very easy for a corporation to just slap a paragraph about sustainability into a brochure to sound socially responsible.
Well, it happens all the time. Greenwashing.
Yeah, greenwashing. But there's a meta detail hidden in the fine print of this document that proves they're actually integrating this philosophy into their daily operations.
The paper itself.
Yes. Even the physical brochure this information is printed on is made using recycled fiber, specifically pre-consumer or post-consumer waste.
It's a really fascinating reflection of their overall methodology. The document explicitly notes that by using less virgin fiber to print the brochure, the very creation of the manual reduces tree harvesting.
And water usage, right?
Yep, water usage, energy consumption, greenhouse gas emissions, and overall pollution.
I also noticed a quick detail on the copyright page. The color green is actually a registered trademark of Sullair.
Which is very fitting for this conversation.
It is. But the true environmental impact here isn't about marketing or even the paper they use.
No, it's much bigger than that.
It's about the compounding effect of predictive maintenance. If you use verified data to keep a machine running at peak efficiency, it naturally draws less electrical power off the grid.
Which reduces emissions instantly.
Right. And if you meticulously track the chemical health of a premium synthetic fluid, you might safely extend its life by several thousand hours.
Meaning less fluid goes to the landfill.
Exactly. You aren't needlessly disposing of hundreds of gallons of industrial chemical waste every single year just because a calendar told you to. It is a holistic approach to efficiency.
And efficiency is really the ultimate form of conservation.
So bring this all back down to earth for you listening right now. This deep dive really demonstrates that true efficiency isn't just about making machines run faster.
Or pushing your equipment harder.
Right. True efficiency is rooted in visibility. By leveraging microscopic chemical tests, lightning-fast lab turnarounds, and expert data translation, operations can extend equipment life, drastically reduce their maintenance budgets, and actively shrink their environmental footprint all at the exact same time.
And that is the core lesson that extends far beyond industrial engineering.
How so?
Well, whether you are responsible for a massive warehouse full of heavy machinery, or you are just trying to optimize your own daily workflows and personal systems, the fundamental truth remains the same.
Data is king.
Exactly. Capturing and utilizing timely, verified data allows you to make highly effective, proactive decisions rather than just sitting back and waiting for things to break.
Which leaves us with a final, provocative thought to consider today.
Let's hear it.
The source text we explore today proves definitively that we possess the technology to meticulously track the invisible chemical degradation of a system to predict its exact point of failure.
Down to the 6-micron particle.
Right. We can spot the microscopic wear and tear of the sand and the rising acidity long before it results in a catastrophic breakdown.
It's almost like time travel.
It really is. So if we can achieve that level of crystal clear predictive certainty for a massive industrial air compressor, What other complex systems in your life, your business, or your community are currently running until they break?
Simply because you aren't paying attention to the right signals.
Exactly, because you aren't capturing the telemetry and the data that is already flowing right in front of you. It's easy to manage the things we can clearly see, but maybe it's time we start running the diagnostics on the hidden systems before the damage is fully done.